In this lesson, we're going to look at diffraction. Now, diffraction is the property whereby waves get bent as they pass through gaps or go around edges of objects. This causes the waves to spread out. So, as an example, we've got some water waves and they're approaching the entrance to a port. So this is the quay side here. So these are quays here. And this is the entrance to the port. And you'll notice that as the waves pass through, they're approaching in this direction. This is the direction of propagation. But as they pass through the entrance, there's a tendency to spread out here as they pass through the entrance to the port. Okay, and this is precisely what we call diffraction. Now, these are the wave fronts of the water waves, and the distance between the wave fronts is the wavelength, lambda. And you'll notice that in this case, the size of the port entrance is quite a bit bigger than the wavelength. But as we start decreasing this gap, so the size of the gap starts to approach the wavelength of the water waves, then the spreading out effect, this diffraction effect, increases. So we get more spreading out here as the wave passes through the entrance. And then when the size of the gap is of the same order as the wavelength of the approaching wave, then the diffracting effect is greatest. So here the size of the gap is more or less the same as the wavelength, and the diffraction of the wave is greatest. The spreading out of the wave is greatest as it passes through that gap. Likewise, if the wave encounters an object, the spreading of the wave around the edge of that object is greatest when the wavelength is of the same order as the size of the object. So just to summarize, diffraction occurs when waves are bent as they pass through gaps or around edges, causing them to spread out. All right? And the effect is greatest when the size of the gap is comparable or similar to the wavelength of the waves. Just to illustrate this, let's take an example from the area of radio transmission. So let's imagine that we've got a TV or FM radio transmitter, right? And it's emitting signals using a wavelength of round about, just say, 20 centimeters. Right? And it wants these signals to reach this house over here, but unfortunately there's a mountain in between. And well, the problem is that the wavelength of the radio waves in this case are a lot less than the object that's in their way. So what's going to happen when they get to the mountain is that they're going to get blocked by the mountain. Now, because the wavelength of these waves are very short, it's 20 centimeters, and they're much shorter than the size of the object that they're encountering, there's going to be a very, very slight amount of diffraction, just bending the waves over the top of the mountain, but they're not going to be able to get to this house here, which wants to receive the signal. Now, what happens, for example, if we use a much longer wavelength, for example, such as long wave? We've replaced our FM TV transmitter with an old-fashioned long wave transmitter, which will emit radio waves with a much longer wavelength of the order of, say, 1 kilometre in wavelength. And let's just draw this schematically. All right, so you've got waves being emitted now with a much longer wavelength. And the wavelength of the long wave radio is now comparable with the size of the mountain. So as a result, the waves will be diffracted around the mountain and be able to reach the house. Now, this is just serving as an illustration. In fact, you can't use long wave to transmit TV signals, and so it's pretty useless in that sense. and we'll talk about how the shortwave radio transmission, or FM radio transmission, gets around this problem of large objects in the next lesson when we talk about electromagnetic radiation. But anyway, the point here is that the diffraction effect is most noticeable when the wavelength is of the same order as the size of the object that is in the way, or the size of the gap through which the waves are passing.